Woohoo! I am live, and we are talking about Math 60 Intermediate Algebra, and we're going on to multiply and divide radicals. And so in this section, we're going to use a bunch of different techniques. We are going to use bare math. Rah! So if you haven't seen my video on bare math, you might want to watch that first because it can be a little disorienting. This is something I've invented. So yeah, I guarantee you have not seen this somewhere else, and it can be a little disorienting the first time you see it. So if you have seen that, thank you. And or if you just want to throw caution to the wind and try this without having any idea what I'm talking about, hey, if it works, it works. Let's math on. Okay, so up to this point, the really funny thing is generally we teach radicals in a circular logic sort of fashion where we basically have already assumed the things I'm about to say, which are that multiplication is your friend. And so what does that mean? Well, it means that if you're multiplying two radicals, radical 8 times radical 2, or square root of 8 times square root of 2, as long as the index matches. So handy dandy highlighter. As long as the index matches, so here we've got, I'm going to highlight something that isn't there, which is, man, if that doesn't summarize modern education, I don't know what it does. So these are both square roots, or just plain old radicals. So we're allowed to smash these together. The 8 times the 2 come together inside the radical, which then allows us to say, wait, even though the square root of 8, or the principal square root of 8, and the square root of 2, principal square root of 2, those are hard on their own. Together, we just get 4, which is going to make things a lot easier. The same is true if we've got cube roots. If we've got 2 cube roots that we're multiplying, you're allowed to just multiply 7 times 5 equals 35 and have a single radical with that same index. Woohoo! In the same way, if you're allowed to multiply, you're also allowed to break it up. So that's what we're doing here. If I've got radical 200, and I'm thinking, I don't know what the square root of 200 is, but I do know what the square root of 100 is, and of course I mean the principal square root, then I've got 100 times 2. I break up the 200 into 2 separate radicals, and then this, the square root of 100, or the principal square root of 100, is 10. So, and this is something that we've already used for bare math. I just didn't introduce it formally yet. So if you've been using bare math, you've been using this property. We just didn't say it out loud. So that's, now that we've said that, that is that. And also we've got this little tiny line. It looks so cute, so adorable sitting there, like it couldn't hurt anyone. This is the most evil, horrible sentence in radical land. The rule for radicals is that if you can simplify, you have to simplify. So radicals are just like fractions. If you can reduce a fraction, you're required to reduce it. If you can simplify a radical, you're required to simplify it. Yay, isn't that exciting? Don't we love that? Oh boy. Okay, so let's go ahead and try a couple of problems. So I'm going to use a combination of techniques. In this first problem, I'm going to go ahead and use bare math. And so I'm going to break this up. First, I'm going to rewrite it because I can't help myself. Okay, now the x's and the y's are not too bad. I'm going to break down the 18 as 2 times 9, and 9 is 3 times 3. If you already know how to deal with 18, you don't have to do it this way. This way is just useful if you're trying to work out exactly how you want to approach it. Okay, so this is a square root. So I want square bare, relatively small square bare. Rawr. And remember, for a square bare, we're going to let 2 numbers run. Yum, 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 yum. And one of them gets out. I'm going to let the 2 x's come out. Yum, 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 yum. And 1 x makes it out. So At this point, you're like, well, wait, this is exactly what we did before. This is square bear land. Yes, but officially, and I'm not going to do this often, but I'll show this to you. Officially, what we've actually done without thinking about it is I have, without writing it out, we have split this into writing it as 3 different parts. The 2 3s get their own radical, the 2 x's get their own radical, and then the leftover pieces, this 2 and this y that don't have friends, so they can't go running through the forest. And again, I cannot caution you strongly enough that if you've never seen bear math, rawr, you have no idea what's going on. So this must be really amusing. So we are, in fact, allowed to do this thing I already told you to do. This part is unnecessary, although if you prefer, you can always write it like this. So this is technically what I'm doing, is I'm splitting this radical into multiple radicals. Woohoo? Woohoo. Okay. Oh, and by the way, yes, this is the final answer. There we go. Hopefully I am not the weakest link. Okay, so now this problem is designed to make you hate bear math. And I wrote it, so this is ironic that I'm writing the problem that's going to convince you that bear math is not the solution. And here's the thing. If I'm actually going to use proper bear math, there are 7 x's. X, 3, 4, 5, 6, 7. There are 11 y's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then there are 9 z's. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh my gosh, it fit. First time in history I drew a radical that was big enough. You can use bear math for this. That is perfectly fine. So what would bear math look like? Well, it would look like taking 2 x's, yum yum. 2 x's, yum yum. 2 x's, yum yum. And 1 x doesn't have a friend, so it just stays in, and so on and so forth. 2 y's, 2 y's, 2 y's, 2 y's, 2 y's. So we've got y. Around this time, I'm starting to doubt that this is actually even math anymore. It's more like accounting. Not that accounting's not fun, but it's not what I set out to teach math, not accounting. Okay, and then z. And you can see pretty quickly that, especially under pressure on a test, something like this would be so easy to make mistakes. So the bear math method, which, although it will work, I don't think it's the best method. I think this is kind of rough. And there was a leftover x and a leftover y and a leftover z. So I would not use this method, but I'm going to finish up this method so we can look at the next method I would use. Let's see, I get 3 x's, I get 1, 2, 3, 4, 5, 5 y's, and I get 1, 2, 3, 4 z's, and then x, y, z. So here's the thing. Wouldn't it be nice if we could have anticipated the 3, the 5, and the 4, so we didn't have to write all this out and possibly make some mistakes? Wouldn't it be nice? So let's look at what we had. We had radical 7, which I'm going to break off from the rest. I'm going to say, this is just x to the 6th times x. And then I'm going to remind you that the square root, this radical, principal square root, is actually just an exponent of 1/2. Notice that three is 1/2 of 6. Same thing here. If I have y to the 11th, that's radical y to the 5th. Oh, sorry, I'm jumping ahead. Y to the 10th times y, right? 11 is y to the 10th times y, which is y to the 5th, right? 5 is 1/2 of 10. And then the leftover y is still left inside. And then radical z to the 9th is really radical z to the 8th times z, which we're allowed to do separately. And so that's z to the 4th times radical z. 1/2 of 8 is 4. So square roots mean you're just taking the exponent and breaking it in half. And what happens when you've got an odd exponent? Well, if you've got an odd exponent, that means there's an extra one that just stays inside because you can only deal with even exponents. So while you're perfectly allowed to do bare math and count them all individually, I would like to encourage you to consider using this half method to end up with, because we can deal with them each separately. That's what this whole chapter is about. We can deal with these separately. So all together, if we have x to the 7th, y to the 11th, and z to the 9th, we've really got x cubed, y to the 5th, z to the 4th, plus some x, or not plus, times, but also the leftover guys, the x, the y, and the z that didn't have buddies, so they can't go running. So your choice, you can approach it either way. But if someone gets kind of nasty on a final exam and puts z to the 432, that's going to be really hard to work through using bare math. So just forewarning about that. Woohoo! Shall we continue? We're 11 minutes. I think we can continue. Let's go ahead. Let's push the bounds of YouTube technology and see if we can get through this next page. So these are some examples of why this is a helpful sort of technique. Square root of 18 or radical 18 and radical 2 or square root of 2. Neither of these are nice, but again, we're allowed to, because they're both radicals, they both have an index of 2. Remember, square roots have an index of 2, so we can rewrite it and combine them together, multiply them inside the radicand, and then I get 36. And radical 36, or the square root of 36, is 6. Life is good. Okay, what about the next one? And I've just been informed that I can't do the usual thing where I go and make that noise because YouTube thinks I am swearing. So I'm going to try not to do that anymore. I got to come up with a new noise for that, but that would be what I would say. I would say, oh no, quelle surprise. What will we do now? We've got the cube root of 9th times radical 2. It really depends on how we approach this. So we can either say that these cannot be multiplied. So sometimes the answer would be already simplified, or so remember this, when the radicals can be rewritten as fractional exponents, I could make this 1/3 equals 2/6. 1/2 equals 3/6. So this is the 6th root of 9 squared times the 6th root of 2 cubed. So altogether, I've got the 6th root of 9 squared times 2 cubed, which is the 6th root of 81 times 8, which is the 6th root of 648. Oh, sorry, you can't quite see that. Now, I got to be honest with you. There aren't a lot of settings where someone will think this is better than this. So you could, from one perspective, say these two indices don't match, so it's already simplified. And there may also be situations where it wants you to go through all this process to get to the 6th root of 648. And then we may be able to simplify this. For example, I could look at 648 and see, okay, I've got 2 times 324, and I've got 2 times 162, 2 times 81, right? There are the 3 2s. 9 times 9, 3 times 3 times 3 times 3. So we look at all of these guys and we say, okay, is there anyone in here that would have 6 buddies to go running, right? For a 6 bear, we need 6 buddies. Okay, there aren't enough of anybody to go running, so this can't be simplified. That is our final form. But again, I am hard pressed to know whether, if you come across a problem like this, whether they're going to say, well, these indices don't match, so it's already simplified, or if they want you to force the issue by coming up with the fact that they are both 6th roots, because we can come up with common denominators. All the hell that comes along with common denominators comes with us into radical land. So it just depends on the application. So there are 2 possibilities. Either we're going to say it's already simplified, or we're going to say it's this bad boy. And it just depends on the setting. You have to talk to your instructor and figure it out. There are 2 options. Okay, but number 3. Number 3 is a lot more of a normal problem, quote unquote. The 4th root of 8x cubed y to the 5th times the 4th root of 4x squared y cubed. The indices match. And so we're allowed to smash them all together. So 8 times 4, x cubed, x squared, y to the 5th, y cubed. So it's the 4th root of 32, x to the 5th, y to the 8th. Ooh, I gave myself way too much room. See, I've tried to change. I've tried to get better at giving myself enough room, and now I'm giving myself way too much. Okay, so here's the rule. If the power inside is bigger than the index, if the exponent is bigger than the index, you need to simplify. So these numbers aren't too big. I'm going to go ahead and use bear math. I happen to know that 32 is 2 to the 5th. Now, if you don't know this, you could very easily do a 2 times 16, 2 times 8, 2 times 4, 2 times 2, right? So you could get that 32 is 2 to the 5th. I've got 5 x's and I've got 8 y's. 4, 5, 6, 7, 8. Oh man, I cannot get this right with the radical sign. Okay, so you may decide, whoa, I'm not going to do this. But I'm going to go ahead and take 4, right? Because this is a 4 bear. I'm going to take my 4 2s. They're going to go running out. And then the bear comes through. And eats all but 1. The x's, I'm going to let 4 go running. Sorry. And oh, this is a big bear. I forgot. The big bear comes and eats all but 1 of the x's. And then with the y's, we got to be really careful. 1, 2, 3, 4, 1, 2, 3, 4, and a piece of bunny fur. 2 y's go running. Well, actually 8 y's. 2 sets of 4 y's go running. And we get y times y. There's a 2 left over here and an x left over here. So it looks like I've got 2xy squared, and then I give it some space because otherwise it can get complicated. This 4 and that 2 can get squished together and end up with something weird. So we're allowed to combine things. When we combine, we will have to simplify. It's like reducing, but not quite. It's called simplifying. But what I also would like to emphasize is right here, if you see the 4th root of x to the 5th, could you imagine that 1x would come out and then 1 would be left over? And if you saw the 4th root of y to the 8th, could you see that 2 would come out and we would be clean? There would be no left over. Hopefully you're starting to anticipate that. You're kind of thinking in terms of indexes or indices being denominators. Okay, woohoo. That was 2 pages. Let's keep going. Math on. I'll see you soon for some more problems.